Hello everyone. We are going to go through some statistical methods to determine significance and difference. So I'm going to talk about these things conceptually. The chapters that we're looking at now from this point in the book forward are pretty statistics-y, if that's a word. And so I'm going to probably tone them down a little bit and have you take a look at these things conceptually and get an understanding of just what they are. If you're going to pursue, for example, an ANOVA in your own research, then you'll need to dig in deeper into what an ANOVA really is and how you set one up. If, however, you're not going to pursue ANOVA or Z-test or T-test or any of the other things that we're going to be talking about from this point forward, then I think it's important for you to know what they are so that you can spot them in other literature and know what they mean. But I don't necessarily think I need you to know how to calculate it. I don't think I need to have you do that. I'll give you the option in the discussion boards, but I'd rather just talk about what these things are conceptually and when you might use them. Okay? So let's go ahead and talk about difference in means in particular. And what we're trying to get at is, how do you know if any groups that you're looking at performed or are being measured, their results are statistically significantly different from each other? So let's talk about some generalities when we're talking about difference. Again, I'd already alluded to the fact that we could look at this from three different ways. One way we can look at it is we can determine if there are statistically significant differences between a sample and a population. We can also look at the difference between two groups, and we can look at the difference between more than two groups and determine if at least two of those groups are statistically significantly different. And I'm going to go through each one of these scenarios. So when we're talking about difference, we're talking about the difference in the means. So what we'll do is we'll go through each of the groups, even the population actually in the first example, and we'll calculate the mean. And then we can use various things like the standard deviation or the standard error. The book goes through all of the mechanics of that, but I'm not going to expect you to know that off the top of your head. So, but we really are talking about the means. Is the mean different from group to group? So we are measuring the mean, and we can see the mean. We can see that the mean between group 1 is different than the mean from group 2, or the mean between the control condition is different from the mean in the treatment condition and the mean in the second treatment condition, but we don't know if it's significant. And the knowledge of whether or not it's significant helps us to determine if our results are meaningful. So we might be able to just look at the mean and compare it and see that it's different, but that doesn't really do anything for us because we don't know if it's significant, and if we don't know if it's significant, we don't really know if it means anything. This will become more clear as we go through more examples. So to determine if a difference in a mean is significant, we have to first calculate the mean, but then we have to look at the scatter around the mean. And when I say scatter around the mean, it's all of the numbers that were used to make up that mean. Are they very similar to the mean? And do they have a very small standard deviation and a very low variance? If that's the case, we call that a tight scatter around the mean. If, however, it's the opposite, and we calculate a mean, but the scatter is really broad, there's a high standard deviation and a high level of variance, then that's a wide scatter around the mean. And that's what can get us into trouble when comparing means, which is why we can't just look at the mean without looking at the scatter, because the scatter can actually tell us quite a bit about that mean. So let's look at this visually. In the example that I'm showing you, on the left side, you have the blue collection of data points. And on the right side, you have the yellow collection of data points. If you look at it, let's imagine that the thick line in the middle of the box, or inside the box, is actually the mean. The means look different here. They look actually quite different. And if we were just going to stop at the mean, we would say, yes, the means are different. But the problem is the scatter around the means. It's a little tighter on the blue side than it is on the yellow side. But if we were trying to say that the yellow treatment had any real significant difference in the blue treatment, and we see that level of scatter around the mean, that's not a conclusion we can support. This is why we need to have both the scatter around the mean, or the standard deviation and variance, and the mean itself to determine whether or not a mean between one group and another is statistically significantly different. So here are some questions that we can address using these three different mechanisms for determining statistically significant difference. The first one is the performance of a group unique? And that's unique compared to everyone else. Now, we won't always have a measure for everyone else, but I'll give you a couple of examples through this slide set where we can actually see the measures for most of the others or a big portion of others, and then determine if a particular group is unique compared to that population. Did a class of students who took a 6-week-long math intervention perform significantly better on the final exam than those that did not participate in the intervention? That's where we're comparing the mean of two groups, and comparing the mean of two groups is best done using t-test. What if we've done an intervention at two levels? For example, we've treated level 1 and level 2, and we also have a control group that didn't get treated. That would be 3 total groups. After our intervention, we want to know if any of the two groups are statistically significantly different, and that would be best done through an ANOVA. Again, why can't we just look at the mean? Remember, we have to look at the scatter around the mean in each of these 3 scenarios. We want to find if we have meaningful differences, and by just looking at the mean, if the scatter is broad or wide around the mean and they overlap, we won't really have meaningful differences. So we want our findings to be useful, and that's really the reason why we're looking for significance. Let's look at an example. Okay, so this is an example where we did an ANOVA. This is comparing 3 levels. And the ANOVA was actually measuring the effect of puppy love on happiness. So what we did is we took 3 groups of individuals. We divided them into control group, a 15-minute group, and a 30-minute group. And we measured their level of happiness. Well, before we measured their level of happiness, we actually gave them the intervention. The intervention was they got to either spend 0 minutes with puppies, they got to spend 15 minutes with puppies, or they got to spend 30 minutes with puppies. And the idea is, are there any significant differences between those 3 conditions? So the happiness measure was a scale of 1 to 10. So when we did our measurements, the control group came out with a mean score of 5.28, mean happiness score. So they're moderately happy. The 15-minute group came out with a mean score of 6.28, so they're a little happier. And the 30-minute group came out with a mean score of 7.57. So when you just look at the means, 5.28 does look pretty different from 6.28, and 6.28 does look pretty different from 7.57. Okay? So does that mean that we have significant differences? Well, we have to look at the scatter around the mean to determine that. So let's go down here and look at, in our control group, we had 7 measures. We had 7 people in the control group, and their measures were 4, 6, 5, 7, 4, 5, and 6. Okay, that's what yielded the 5.28 mean control, our control mean. For our 15-minute group, the measures were 6, 4, 5, 7, 8, 5, and 9, and that yielded the mean of 6.28. The problem is when you look at this, the scores in the 15-minute group look an awful lot like the scores in the control group. So when we were to compare the control group to the 15-minute group, we probably aren't going to find that there is a statistically significant difference or that there was a significant impact of the intervention at 15 minutes. That's why we're looking for the significance. We want to know if we see significance in the numbers, that means that the treatment or the intervention may have had a significant impact. Let's move on to the 30-minute treatment. The 30-minute group had scores of 7, 8, 8, 6, 9, 8, and 7. And while there is some overlap, in fact there is quite a bit of overlap between the 15-minute and the 30-minute group, we still are unsure as to whether or not that is a significant difference. The mean is 7.57, which is quite a bit higher than 6.28, but with so many numbers overlapping, we just don't know if there's a statistically significant difference. So let's take a look at this visually. Here is a representation of the control group. The range runs from 4 to 6, and we start down here at 4, and we hit up here at 6, which is the top of the range. If you look over at the 15-minute group, the range of 4 to 6 falls within the range of 4 to 9, which is making up the 15-minute group. You really cannot say that there's any statistically significant difference here. The p-value will let us know. And then if we look at the next group, we can say that, well, the 15-minute group also encompasses the 30-minute group, so there's probably no significant difference here either. We can't say with a reasonable amount of certainty that the means are different. What we can say, however, is and we would be using ANOVA for this, with ANOVA we're looking for the difference between any 2 of our 3 groups. And in that case, the control group is It's probably statistically significant than the mean group because they only overlap by a tiny bit. That's at 6. But again, when we run the statistical test, the statistics will bear it out. And I'll talk about that next. But this is one example where from control to 15 minutes, no significance. From 15 minutes to 30 minutes, no significant difference. But from control to 30 minutes, there was a significant difference. So this could be a case where the intervention just wasn't long enough for us to see a significant change. So this is just a recap of what I was talking about. The control to 15 minutes, no significance. 15 to 30, no. But control to 30 minutes is likely. Okay, now how do we know for sure that it's actually significant? Well, all three of the tests that we're talking about, z-test, t-test, and ANOVA, will give you a p-value. And they will give you a p-value that means different things. I don't want you to have to worry about how that p-value is calculated. It's usually done through statistical software. You just need to decide what your p-value threshold is, or read what the researcher decided the p-value threshold was. Again, it's typically going to be 0.05. So when the results from the z-test, the t-test, or the ANOVA come back, and they are less than 0.05, and that is the threshold that the researcher has selected, we then know that we have a significant result. Let's go through some examples. First one for z-test. Okay, a z-test, again, is we're comparing a new group to an established population. So let's imagine that we have an incoming class of graduate students. And that incoming class of graduate students all took the GRE, the Graduate Records Examination Score. What we want to know is this group seems like they're really sharp, and it seems like these scores are kind of high. So we want to know, is the mean score of that group different statistically? Is it unique from the 20 years of history that we have of all the other students that came in and who had taken the GRE? So we're in this case comparing a group to a population, and so we use z-test, and it will tell us how different that group is relative to the population. It'll also tell us if it's significant because the z-test gives us a p-value, and the p-value, again, we decide the threshold, but if the p-value falls below our threshold, then we know that our test is significant, that this group of students, their GRE scores are significantly different than the established population over the last 20 years. T-test. T-test, remember, we're comparing two groups. So one group to another group, are they statistically significantly different? Here's an example, a real-world example that we just did. We collected end-of-course evaluations at CU for the 2018 to 2019 academic year. These numbers, by the way, are fictitious. I just made them up, so but they illustrate our purpose. For the School of Management, we had 354 classes that were taught over that year, and the mean end-of-course evaluation score is 3.24. For the School of Applied Leadership, we had N equals 122, so 122 classes were taught from that school over the last academic year, and the mean was 3.51. Is that difference statistically significant? Well, we're going to run a t-test, and the t-test is going to provide us with a t-statistic that is a measure of the difference, but it's also going to provide us with a p-value. If we've established a p-value threshold of 0.05, and we fall below that p-value threshold, then the difference between the School of Management and the mean for the School of Applied Leadership is statistically significant. For the third example, we'll talk about ANOVA. Let's imagine for a second that we're testing a reading intervention, and we're looking at whether or not the intervention had any impact on the standardized scores that the students take at the end of the year, the standardized tests that the students take at the end of the year. In our control group, we really didn't do anything different. We just gave them the standard reading instruction, and their mean scores came in at 82.5%. For group 1, we gave them the standard reading instruction and an intervention that went on for a half year. Their mean scores came in at 85.6%. For group 2, the standard reading instruction was given, but we gave them the intervention for the full year, and their scores came in at 90.7%. If you just look at the means, that could be a pretty exciting result. But you've got to determine whether or not it's statistically significant. Because if the scatters for those three means greatly overlap, there's not significance. It's just a matter of chance that we got those scores. So is the difference between any of these two groups statistically significant? ANOVA does something a little different. Whereas t-test and z-test will give you a straight-up z-score, and it will give you a z-statistic or t-statistic, ANOVA gives you an F ratio, an F value, or an F statistic. And what that F value is, and I'm not going to go into too much detail about it because you could spend days trying to figure out how it's actually calculated, but it is the ratio of the amount of variance that is explained by the ANOVA divided by the amount of variance that is not explained. So when you have a high F value, it means that most of your variance was explained by your ANOVA. When you have a low F value, it means most of it was not explained. ANOVA will also give you a p-value, but this p-value actually applies to the F value. So assume that we have a high F value. It's like F value of 10. It means that there's 10 times more explained variance than there is non-explained variance. And the p-value is 0.001. That means that that F value is very significant. Hence, the ANOVA is significant. Remember, however, though, ANOVA will only tell you that of the 3 or more groups that are in your ANOVA, 2 of them, at least, are statistically significantly different. If you need to find out which ones are statistically significantly different, then there's a whole other process for doing that. And I'm not going to go into that. But ANOVA will tell you that there is a difference, that your intervention did likely have an impact. So, always remember when you're evaluating the literature, if you're evaluating an article and you see z-test, remember that the researcher is comparing the mean of one sample against a population. If you see that the researcher is using t-test, it means that he or she or they are comparing the means of 2 sample groups. And if you see that the researchers are using ANOVA, the researcher is comparing means across more than 2 groups and determining whether or not there's a significant difference in any of the 2 groups. Just also be aware that there are other forms of ANOVA that exist, or many forms of ANOVA. Ones that you might run into could be ANCOVA. ANCOVA is just basically ANOVA with the covariate. And what that basically means is that I'm explaining differences between my groups, but I'm also attributing that difference to some other variable. So it's a covariate. There's repeated measures ANOVA. What we've been talking about in this presentation has been independent ANOVA, where all of the people in each of the groups is different. If there's repeated measures ANOVA, then it's possible that we are measuring the same group of people, but just at different points. And that would be a repeated measures ANOVA. And then there's factorial ANOVA. What I showed you was a 1-factor ANOVA. We were only looking at one variable. But what if we want to look at the interactivity between 2 variables or more variables? That would be a factorial ANOVA. So as long as you understand the basic concepts of ANOVA, I think you'll be fine. But again, to summarize, z-test, t-test, and ANOVA are ways to determine if there is statistically significant differences between groups.